have a story to tell you, okay? And the story has to do with peanut butter sandwiches, okay? So let's say that you normally have 2 slices of bread and you have X amount of peanut butter, and you said, this is the perfect peanut butter sandwich. You get it? And then I noticed that you bring let's say you bring enough bread to make 10 sandwiches, and you bring enough peanut butter to make 10 sandwiches. What do you think is going to be made? 10 perfect peanut butter sandwiches. Everybody get it? But let's say that you want to feed hungry people, and you said, I'm gonna do this. I'm putting my resume and all that kind of stuff. And so you get a bunch of people and say, go to all these stores and ask them for a peanut butter. And I want you guys to go to these stores and ask for any bread they could donate, okay? And so meet here on Saturday. We're gonna make enough peanut butter sandwiches to feed 200 people. Okay, so let's say who's gonna do this? Caroline. Caroline shows up and she's here. She can't wait. She's got the tables all ready, okay? And what happens is, here's the next truck comes in, another truck comes in, and it's like, wow, the bread. This got huge amounts of bread. And I said, wow. He said, look what we did. We have enough bread to make 300 sandwiches. She says, yes, we're going to make 300 sandwiches. And then the 2 people that are supposed to get the peanut butter, one of them forgot all about it, and the other one got to stop at one store, and they got 2 jars of peanut butter. Okay, ready? You have enough bread to make 300 peanut butter sandwiches. Is that going to happen? No. When you start using the 2 jars of peanut butter, after about 15, 20 sandwiches, it's going to be gone. You had enough bread for 300 sandwiches. You did not have enough peanut butter for 300 sandwiches, right? So which material would be called the limiting reagent or reactant? I think your book might say the word reactant. Which one is going to limit how many peanut butter sandwiches are made? The peanut butter. Now, I want you to think about this, okay? This is the same kind of problem we've been doing, except I'm going to show you a little trick that works. And I've had students come back from college and said, how do you know about that? I just made this up. It worked for me. Because I don't think anybody taught me how to do this when I was younger. So let's try around section 9.3, and I'll help you do your homework on, okay? Here we go. How many moles of water can be made from 4 moles of oxygen gas and 16 moles of hydrogen gas? Okay. So we got oxygen gas plus hydrogen gas, and we're going to make water. Okay, now, don't do any stoichiometry unless you have a balanced equation, so go ahead and balance it. Okay, so rebalance it. So you have 2 O's here, only 1 here. I'll fix that. Okay, is it okay? All right, let's do, since I'm going to let you shortcut on the limiting react, I'm going to let you shortcut on these. Let me show you how this works. What's the molar mass for O2? What's the molar mass for O2? Everybody. 32 grams. Okay, what about for H2? All right, and what about H2O? Okay, I'm ready to do my shortcut. Now here's what we have. Let's write down the given. What's it say here? I have 4 moles of oxygen gas. Well, I'm in the mole world down here, aren't I? Now I'm going to show you a little trick. Okay? This could be like the peanut butter. I have enough peanut butter that this should happen, and tell me what this box would be. Don't write in there, though. And what box here? Ready? What's it? See this? Gotta get bigger. So what's this going to be? 8? Okay, let's write that in there real faintly. There you go. And then what's this going to be? Matchy. Is that right? Oh, yes. I brought enough peanut butter we are going to make 8 peanut butter sandwiches. Wait a minute. Let's see. How much hydrogen gas did you bring? This story is seen through the eyes of how much peanut butter was brought. But now we need to see the story through the eyes of how much how many bread was brought, okay? Now, how much bread was brought? 16 moles. Now, what I'm going to do, I'll show you a little trick. Anytime you have a question, a stoichiometry problem, if they ever tell you how many grams of one and how many grams of another, you have to do this. You have to find the limiting reactant. What if they tell you how many moles of one and how many moles of another? You got to find out who you're going to run out of first. So a little bell goes off in my head. Whenever I see a problem, it says, you're going to give me grams of that and grams of that? Ding, 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 ding. I'm going to write 2 rows of boxes. 2 rows of boxes. And then what I'm going to do is I'm going to put a little asterisk. See this here? This is how much I actually was brought. 4 units of peanut butter were brought and 16 breads. Get it? Now, this is what does this number represent? It says, if you want to use up all the peanut butter, you had to bring me what? 8 units of bread. Well, how much did you bring me? And the asterisk says what? So, are you going to run out of bread first? No. If the reactant that is not going to run out of first is called the reactant that's in excess. So, you're not going to run out of hydrogen first. You're going to run out of this one. So, therefore, the limiting reactant, and they call reagent, same thing, is oxygen. Now, how do I know that? Okay, let's try it again. I started with 4 moles of O2, and the balance equation said I would need 8 moles of hydrogen. I need this many in order for this to happen. Well, how much did you bring? Oh, I got plenty of hydrogen. You're not going to run out of me first. You must be the limiting reagent. Now, what that means is, which is going to happen? Are you going to make this many peanut butter sandwiches or this many? If you run out of this first, this is what's going to happen. So whatever row the limiting reactant is in, that is the storyline. You will make this many moles of water. All right, let's try it the other way now. Let's pretend that I had this up here. Hey, I brought 16 moles of bread. And, I better figure out how much peanut butter I would need to use up all the bread. How much? Gotta get smaller. Gotta get smaller. What are you going to multiply by? I'm going this way. What do you multiply by? 1 over 2 or 2 over 1? 1 over 2. Oh, 8. See? Hey, you know what? Here's the story. I brought this much bread, this much hydrogen. You want to use all the hydrogen up? You better bring me 8 units of oxygen. Did you? Did you? No. I only brought 4. What? I need 8 to use all of it? No. I'm sorry. I guess you're going to run out of me first, aren't you? Now, whatever row the limiting reactant is in, that is what's going to happen. But wait. I came here thinking we were going to make 16 sandwiches. That is not going to happen. Is it? Why not? Why would they not be making 16 sandwiches? What do you think? Danielle, you know. This says, I'm going to make 16 sandwiches. Why is not? What? Well, yeah, or oxygen, right? So you're going to run out of oxygen before you run out of bread, aren't you? And that's how you do limiting reactant problems. So if you're doing this on homework, it says here, What is the limiting reactant? What's the answer? Is it oxygen? Oh, by the way, reactants are on the left side of the arrow, aren't they? Which one's the limiting reactant? It's either you or it's you. Which one? Well, it's you. It's this guy, isn't it? That's how you answer that one. That was pretty easy. Okay. Now let's do the next one. It's called number 2, right? Number 2. Just calculate the mass of water produced from the reaction of blah 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 blah. Okay. Well, you know the good news. Oh, thank you very much for using the same equation. Oh, I'll take it. I'll take it. So everybody start with the same balance equation? Now I keep looking at your faces. Your faces have to tell me what's going on, okay? Are you okay with this equation? Okay, now what are they going to give me? What information are they give me now? 24 grams? I'm going to put that up here. Isn't that where that belongs? Isn't that where? Okay. And what's the other one say? 160 grams? All right. Now, ready? How did I know that this problem, I had to draw 2 rows of boxes? How did I know it was a limiting reactant problem? Because they told me how much peanut butter and they told me how much jelly. I had to figure out who was going to run out of first, right? So if they give me moles of each, I have to do this. What if they give you grams of each? Is there still a limiting reactant? Yes. If you're going to tell me either moles or grams of the 2 reactants, I got to figure out who you're going to run out of first. And all you got to do is do this. Watch. I'll show you how to do this. This is the first time you've done it. Just draw 2 rows of boxes. One is the story as seen through the eyes of the peanut butter, and one through the jelly. I'm not doing jelly, bread. Okay, now, so step number 1, draw 2 rows of boxes. Okay? Now, this is the hard part. This is what people forget. I'm going to put an asterisk, right? I'm going to put a star here. That star says, when I convert that into moles, that's not how many moles you'd like to have. That's how many moles you do have. Now here, I'll use another. Like smiley faces? Okay, I'll do that. I'll put that here. Yeah, there you go. Now, notice when I change this to moles, I will not put it in the same rows. Everybody get that? So one is the story as seen through the eyes of the peanut butter, and one through the eyes of the bread. So, can everybody remember that? All right, now let's do some shortcuts. Everybody ready for shortcuts? Let's do some, we already have molar masses. Ready? When you want to go down the mole world, what do? Okay, calculators, go. Go, ready? What am I going to put right there? If you want to go down the mole world, you divide by the molar mass. What is it? 5 even? Oh, is it? Okay, that's it. 5.00. 3 sig figs, we'll do that. Okay, now, everybody write that? Okay, let's do the other one. Ready? Let's change that to moles and put it in another row. When you down the mole world, you divide by molar mass. What's this going to be? 12. All right, now I'm ready. I am ready to find out who the limiting reagent is, okay? The reactant, same thing. Now, this is the first day you've heard this, so raise your hand if you know exactly what to do right now. Good. Only one person raised their hand, 2. That means the rest of you are, so I'm still learning this. Okay? Here's how we do it. I want to tell the story in terms of the eyes of the peanut butter. So I don't want you to look down here at all, okay? I have 5 moles of O2. How many moles of H2 would I need to completely react with me? Well, how am I supposed to know that? Watch up here. 1, 2. 1, 2. Gotta get bigger. Multiply by 2 over 1. 10. Okay, so everybody with me? Okay, forget you even know that, okay? If it was just in terms of the peanut butter, I would need 10 moles of hydrogen, and then we would make up how many? We'd end up making 10 sandwiches. Look, matchy matchy. Okay, question is that going to happen? I don't know. I'll tell you in just a second. Watch now. I call this the 3-box method. In 3 boxes, I will be able to tell you who the limiting reaction is. Are you ready? I'll start right here. I have 5 moles of oxygen. I would need how many to use this all up? How many hydrogens do I need? 10 moles. Did you bring it? Did you bring 10 moles? I got your 10 moles. I got you covered and more. I am the one who will be in excess. Don't you dare call me the limiting reactant. I'm not the limiting reactant. You are. You are limiting reactant. Oxygen, you are. Okay, so what's going to happen? Whatever row that the limiting reactant is in, see a little star? That is what's going to happen. Now, let's pretend that the way you read the problem, you started with the 12. All right, let's do it this way. Ready? 3-box method. I know I brought 12 moles of hydrogen. How many moles of oxygen would I need to completely react with me? Let's look up here. I'm going sideways, right? When you go sideways, you look at the coefficients. 2, 1, 2, 1. Gotta get smaller. Now, what's this going to be? Is that 6? I keep looking at your faces like either completely lost or you catch on really easy. Here we go. Let's tell the story. I'm going to pretend I started with this number. Hey, I brought 12 moles of hydrogen, and I need 6 moles of oxygen to completely react with me. Did you bring 6? I only brought 5. Only 6. I only brought 5. Well, then you're going to limit how many sandwiches get made. Yeah, sorry. Whether I start here and do the 3 boxes like this, or I start here and do the 3 boxes, it comes out the same answer, right? You're the limiting reactant. How many sandwiches are going to be made? I really thought 12 sandwiches are going to be made. It's not going to happen. It's not going to happen. Only 10 are going to be made. Now, here's the question it says. Calculate the mass of water. Oh, we're not even done yet. Calculate the mass of water. But I had to find out how many moles of water really were going to be made. Now let's do the shortcut. Ready? When you want to come up out of the mole world, what do? What's the shortcut? If you come up out of the mole world, you do what? Multiply by the molar mass. Molar mass of water is 18. What's 10 times 18? 180. Wow, that wasn't too bad. Okay. You guys are honor students. So I'm going to ask you a hard question. This is a hard one. Last week, I want you to add these up and compare it to that number there. What is the total mass of the reactants? What's the mass of the reactants? 184 grams. What is the mass of the product? 180. You might say to yourself, well, that's kind of close, rounding. No, that's not very close. Why did it almost exact last week, but not on this one? Okay? Let's see if anybody's really up on it today. If you're a pretty good thinker, why are these off? I try to tell you about companies out there that use stoichiometry. If you have 2 companies and they're both making the same product, what do you just say? Hey, let's put a little bit of this and a little bit of that in there. Is that what you do? What do you think?
Because when we were doing stuff last week, we had exactly what we needed. And so it was going to work out regardless. But now we don't have exactly what we need. One of them has more. So
So let's take a look at this guy right here, right? Watch right here. Some of you are going to have this aha moment. A little light bulb come on and said, ooh. All right. Here's what I'm asking on a test one day. How many moles of hydrogen were in excess? That means they didn't get used. They didn't react. How many moles of hydrogen were in excess? Now see how I organize everything? Because everything's organized, I should be able to tell this time. Watch. I brought 12 moles of that. Did you use them? Did you use all 12? No. No, I only used what? Well, then what? Well, you have 2 moles of H2 in excess. How much is that weigh? Remember a shortcut? How much does that weigh? How many moles were in excess? 2. How many grams were in excess? Oh. So the moles of product, the grams of product were 180, but there's still 4 that didn't react at all. That's 184. Okay, what do you think about that? A little too that's pretty neat how that works. So I wouldn't expect these numbers to match on a limiting reactant problem because you're going to have one of them is going to be left over. It's like that. All right, number 3. I want you to sit close to somebody. Not super close, you know what I mean. I'd like you to do number 3. All right, go find a partner and see if you can do number 3. Do number 3. I'm going to do it while you guys are sitting here. Oh, by the way, I think the author made a little mistake here on number 3. He should have said burning of 18 grams of carbon actually produced. He should have said actually produced 55 grams of carbon dioxide. What is the theoretical yield? And then what is the percent yield? All right, what do you think? How many people have a good partner? They're sitting with a good partner. Uh-oh. You didn't raise your hand?
Oh, I didn't see that it says carbon dioxide. Okay, carbon dioxide is 55. So 55 divided by, oh wait. Yeah, 55 divided by what's CO2? Yeah. I think it's 44. Pretty sure it's 44. 1.2. I don't know. It's just like the this.
theoretical.
50. I just know that 55.
That's the percent weight.
All right, how we doing? How we doing?
Did they tell you what oxygen? How do you find that?
You find out the moles of carbon. It's easy to divide, and then it's the same. And you multiply.
So, hey, everybody, let's pretend that everybody's confused. Oh, I don't want to pretend. Let's pretend that everybody's confused. And let's start out simple. And did everybody do the balance equation? Carbon plus oxygen yields what? Now, what makes this simple is the coefficients are all 1, right? That makes it, did everybody get that far? Now, I'm trying to show you how to organize. I'm going to put 18 grams here, and then I'm going to find out, in theoretically, how many grams you could have gotten. So let's see how to do that. Ready? Can I go from here just right to here? Can I just do that? No, there's 3 in the way. So here we go. Shortcut. Are you ready for shortcut? When you want to go down the mole world, you do what? Divide by the molar mass. So what's 18 divided by 12?
Should be 60.
That's the
Did everybody get that far? All right. Wait, 18 divided by what? The molar mass of carbon is what, 12? Okay. So everybody should, did everybody get 1.5?
how do you
If not, tell your partner. What's the matter with you? All right, now, what we're going to go here is we're going to go all the way over. Uh-oh. 1, matchy, matchy. Did everybody get that far? Wait, did you get that far? I got to know. Everybody get that far? Now, when you come up out of the mole world, what do? Multiply by the molar mass of CO2. What's 44 times 1.5? I'll bet it's 44 plus 22. Don't you think so? How many is that? Now, we did this problem last week. Man, that's simple. I can do it with shortcut. It's even faster, isn't it? So the question is, if everything was perfect and you had no error, what's the theoretical yield? 66. What's percent yield? What is the theoretical yield? 66 grams, right? That's answer number 1. What is the percent yield? Okay, hang on just a minute. I need the actual, somebody has to actually do the experiment. Actual yield over what? Theoretical
actually
yield times 100. That just moves the decimal over. And so it looks like we're going to do, what was the actual yield? Where is that guy? There he is. 55. Hey, when you actually did it, you got 55 grams. But you know what? In a perfect world, you could have gotten what? What could you gotten in a perfect world? 66. You're not perfect. Okay, I don't expect it. You're not going to get perfect. Let's try it. What's 55 divided by 66 times 100? That means move the decimal over. What do you got? You got it? What do you got?
83.3.
One more time.
83.3%.
367. Ooh, 367?
No, 6.3.
Wait. Say it again.
83.
83.3%.
61? Why you give me all those numbers?
Percent.
She's saying 80%.
Percent.
Yeah.
Is that it? Thank you. Sorry. All right, how many people got that right?
Yes.
Yes.
Now guess what? what did we not do that time? Was this a limiting reactant problem? No. How do you know if it's limiting reactant? You either have to give me grams of both reactants or what? Moles of both reactants. I didn't do it. All right, now together in the same team, if you can do number 4, I'll know that you understand today's lesson with limiting reactant. All right, let's do number 4 together. You do it. All right, number 4.
Okay, so ignoring the.
Oh, that's not limiting reactant. Darn it.
It's.
Darn it.
Wait, I don't know. Yes. No, it's the other way around. It's decomposition. It's HCl. That makes H. And you balance it. Okay. So it's 2 HCl. Okay, so 20 hydrogen chloride. Balance 20. And it produces 30 chlorine gas.
One, what's the chlorine? Chlorine's like 35, right?
It's 35.4, so that times 2. 32. CO2.
Okay.
70.8.
All right. Now, I will help you a little bit on this. I didn't write this, but the author thought that you would be able to figure this out. So if you decompose HCl, what are you going to get? If you decompose HCl, what are you going to get? H and Cl, is that right? But guess what? Both of those are what? Diatomic elements. So did everybody put that down? So when you balance it, notice that we had to put a 2 here. See that?
70, 35.
Okay, let's do some molar masses.
What do you get?
It's 7.5, 0.707.
0.070.
0.707.
707. Okay. Let's see, and then you gotta multiply, or you divide times 2, right?
No. Wait.
Yeah, because it's coefficient 2 divided by 2. It's 35 or 0.3535. And they're matching. Okay. What are we trying to do? And then we multiply, so I'll multiply.
2.6.
Well, that times 2 would just be.
It doesn't give us the
It's,
actual.
so hydrogen's just 0.707.
It doesn't?
Yeah, it does. I'm just not using the right word.
Yeah.
I'm not using it.
All right. Everybody ready? Let's take a look. Here's the balanced equation. And the way I've tried to get you to organize it, I'm going to put grams up here. They want me to, I better find the theoretical grams, right? I better find the theoretical yield for Cl2. But anyway, so how do we do that? Remember, I can't go from here to here because there's a tree in the way. So I go whoop, down, and whoop, we're going across. All right, are you ready? How do you do this? 25.8, when you go down the mole world, you divide by the molar mass. What's the molar mass of HCl? I do that right now, right? What's 25.8 divided by the molar mass of HCl? What do you get, Madeline? When you go down the mole world, you divide by the molar mass of HCl. So what's 25.8 divided by 36.5? Okay. Had you guys not done this already? Ah. All right, what's 25.8 divided by 36.5? 0.7 what? 06? Okay. So the next number after the 6 is not 5 or higher, is it?
Yes, it puts 707.
So we should say 707? Okay, everybody got that? We round to 3 sig figs. Don't chop it off. Did everybody get 0.707? Okay, now, ready? Let's go over. Whoa! Whoa, we're sliding across the mole world. 2, 1, 2. Gotta get smaller. Gotta get smaller. Multiply by what? 2 over 1 or 1 over 2? 1/2, right? What do you get? 0.35, what? 3? What's the next number after that?
3.
Okay, good. Are you okay on that? When you go sideways in the mole world, all you look at is the coefficients, don't you? They're called the mole ratio. Yeah. 2, 1. Is this twice as big as that? Yeah. Is that twice as big as that? Yeah. Now, one more. Let's get up here. How do you come up out of the mole world? Multiply by the molar mass. What's the molar mass of Cl2? Should be 71, shouldn't it? So what do you have up here? Max, you have this one?
No, I don't.
Okay. Do you have, Ethan, do you have this one?
We had.
It'd be 0.353 times 71.
Is that? Wait, it's 25. Yeah, 25.
25? Oh, 21?
25.
25 even? The next number is 0? 0.1? You always have 3 sig figs, okay? Now, did everybody get that? Just say no, I didn't. I mean, is everybody getting 25.1? Okay, now guess what? What is this called? Actual yield or theoretical? I didn't see you getting equipment out. You didn't actually do the experiment. You didn't get that number from actually doing it, did you? All right, so how to do percent yield? What's the actual yield? Uh-oh. Here, go back to my problem. Ah, there it is. 13.6. It said that the actual yield was 13.6. Ah, wow, you stink. You could have gotten 25. What'd you get? 13.6. Out of what? You could have gotten 25.1. All right, what's the percent yield? Elizabeth, do you have it?
I'm at 51.8%.
51 point what?
8.
Woohoo, not great. But you know what? There actually are some experiments. There are some reactions that no matter what you do, it's difficult to get more than 50% yield. And again, that's I'll tell you a 1-minute story. A lot of companies in the United States, they know if you have 51% yield, they know that's not great. They know you're wasting a lot of money, but it's the best I can do, and our competing company is the best they can do. So what they could do is hire a bunch of American chemists at a pretty high rate and say, work all year or work for the next 2 months. I want you to find me a catalyst. Find me a catalyst that'll make this reaction take place at a faster rate, so I can at least make more of this material in a 24-hour period, and I can outcompete my company, another company. What do? I'm not going to like this story. They go to Europe and India, and they said, you got some chemists there? Oh, yeah. How much do you have to pay them? Not very much. You mean they'll work like day and night for like 2 months, 3 months? Yeah. And it only costs me this much? And that's what they do. And then they try to find a catalyst. And if they find a catalyst, they tell them what it is, and the company says, here's your money. Thank you. And then this company now can make that product faster and faster with a catalyst, and they didn't have to pay very much, and didn't have to pay a lot of American chemists a lot of money. You know what? It's okay. I think it's okay. You know why? They could have said no. But where they were at, the amount of money they were getting paid, that was a good amount for them over there. It wouldn't have been a good amount here. But they wouldn't have gotten that job if they said, I'll do it. I'll do that job for that much. Then they got paid. They got what they wanted. And the American companies got what they wanted, and they saved money. Whether you like that or not. That's what they can do. What do you think? What do you think? All right, I tell you what, I'm not going to do anything new. So what I'd like you to do is work on your homework, and I won't see you till Thursday. So You should be able to get it done by Thursday, I would think. Okay, let's go ahead. You have the